the lead from uranium-235, they actually give ages between 1 and 2 billion years. This is well known in the geologic literature. It's not something that a creationist dreamed up. That diagram actually comes from one of the 2 textbooks that's used in every university around the world to teach geochronology, the dating of rocks, to geology students. So this comes straight out of their own. They recognise, and they call this the lead isotope paradox, that all these islands with recent lava flows that can be historically eyeballed give ages of 1 to 2 billion years. So we can see that this assumption, all the daughter derived from the parent, is violated by inheritance from the mantle. We've got examples where we know the true ages of the rock, and in fact we get wrong ages as a result of these dating methods. What about assumption number 2? No other process has affected the parent-daughter relationship other than radioactive decay. Well, if we go to New Zealand, it's got very volcanically active areas in the North Island, the central North Island, the Taupo volcanic zone. Mount Ruapeo is an active volcano, and Mount Ngauruhoe, just to the north of it, was up until recently New Zealand's most active volcano. And there's Mount Ngauruhoe in the foreground and Mount Ruapeo in the distance. By the way, hands up those who saw the movie The Lord of the Rings. Okay, that was Mount Doom in The Lord of the Rings. And there it is up close. The last eruption was in 1975. It's actually been dormant. But prior to that, it erupted every 10 to 15 years on a regular basis. And you can see from the slopes, some areas are grassed and some are not. You can see different colours on the slopes of the volcano. And the volcanologists and geologists know the exact dates of many of these lava flows. The exact dates. In fact, here's a map of some of the more recent lava flows. There was quite a few in 1954 and 55. You actually knew the day, the month and the day in which the eruption occurred. And so it was very easy to go in there and actually choose samples from specific lava flows, the date of the eruption we knew exactly. So I collected samples from the 1949 flow there, number 1 on that list, from the 1975 avalanche deposits, from the June 30, 1954 flow, one of the July flows, but there were 5 different lava flows I collected samples from. And we knew the exact dates of those flows. And yet they gave potassium-argon model ages up to 3.5 million years for rocks that were less than, at the time, were only 50 years old or less. Now the answer is, of course, that they gave those ages like the ones from Mount St Helens because there was extra argon, excess argon, inherited from the mantle source of these lava flows. Interestingly, the rubidium-strontium isochron age was 133 million years for these samples, although there was a big error margin. Interestingly, the geologists also used the daughter atoms, compare the different daughter atoms to test whether there has been contamination. And these lavas at Mount Ngauruhoe are not basalt, they're of a lava called andesite, named after the Andes Mountains. Okay? And they figured out why they were not basalt lavas when in other parts of the Pacific you get basalt lavas. Why were these andesite lavas? Well, it was because, and this is a very technical diagram comparing the different daughter isotopes. The bottom diagram is lead versus neodymium. The top diagram is lead versus strontium. And this has all been published in technical papers for those of you who want to follow up the details. But this plot shows how you can demonstrate there was between 5 and 10% contamination of an original basalt lava to produce these andesites. The composition of an original basalt had been contaminated. So if the lava had been contaminated, therefore you can't trust the radioactive dates. You've assumed no contamination, but now we can demonstrate contamination. And the contamination was due to the fact that the Pacific Ocean floor is actually being pushed down under New Zealand. The basalt is being produced at the base of the mantle. The red area is the mantle, but some of the material that's being taken down into underneath New Zealand includes some of the ocean floor sediments. They're actually being pulled down into the Earth's mantle with the ocean floor, and it's that which has contaminated the basalt to make the andesite lavas. Here's another example of contamination. This was also published in the first volume of the Rate Research. This comes straight out of the secular literature. They took a grain of a mineral, and they actually, with a very small beam of ions, an electron beam, to test spots, very tiny spots on this crystal. At the edge of the crystal, you can see there the edge sample of spot number 2 gave an argon-argon age, which is a variation of the potassium-argon dating method, of almost around 500 million years. And the further you went into the grain, the younger the grain became. And so you got in here, once you got in about 100 millionths of a metre, a micron, 100 microns, the age had dropped to about 150 million years. Why was that? Well, it was because the outer edge of the mineral had absorbed argon, which was moving through the rock, and it had been diffused and permeated into the crystal to make it look older. So argon is a gas that moves around, and so it can cause contamination inside the Earth's crust. In fact, here is dating of individual felspar grains from rocks in central parts of Australia that actually give argon-argon ages up to over 9 billion years, because of having extra argon in them, inherited in them. Here's an example here in Colorado, in fact, where a granite had intruded into schists, other crystalline rocks, metamorphic rocks, and what had happened is that the heat and the fluids from the granite actually perturb, change, make the ages in the surrounding rock younger. When you go out several miles from this granite, the age is around 1200 to 1400 million years. The age of the granite is supposed to be about 100 million years or less. And see what happens. The heat and the hot water from the granite has actually changed the ages in the surrounding rocks, brought them lower. So heat and fluids have actually perturbed the system and caused contamination.
Was the new rock absorbing argon Australian?
No, because the water flow was out of it.
Okay.
So the heat and water was coming out of it. So the flow was away from the younger rock into the older rock. And you can see for up to 1,000 feet, there was significant reduction in the potassium-argon ages and in some of the rubidium-strontium ages on some of the minerals in the surrounding rocks. So you can imagine that's heat and hot water has altered these ages. So what's going to happen to rocks that are in the ground for a long time when geologists aren't there to monitor that nothing has happened to cause changes in the ages over the supposed millions of years? In the same situation here in Colorado, now we're looking at the uranium, lead and lead ages, and again you can see they're significantly altered by the heat and the fluids from that granite. This is one of my favourites. This diagram and several related diagrams are in the first rate book. This again these are all examples out of the conventional scientific literature. This is not results produced by creationists. So I'm just demonstrating that this is well documented in the scientific literature, the problems with these methods. In this instance, they took individual crystals of a mineral that they could date using uranium lead dating by shining a beam of ions, a beam like electrons, onto the crystal surface of a flat surface of this crystal. They found that if they changed the angle of the crystal so it wasn't perpendicular to the beam, they perturbed the age of the crystal by several 100 million years, just by changing the way the beam shined on the surface of the crystal.
What kind of a dating method is that, using a beam?
It's called the ion microprobe. And the most sophisticated version is called a shrimp, and it was actually, the technique was developed in Australia at the Australian National University in Canberra. It stands for a high sensitive, high-resolution ion microprobe. Rather than electrons, you shine a beam of ions, ION, onto the crystal surface.
So do they think that's a good method of dating?
Yes, it's actually the most used method now. You may have seen in the literature where they've supposedly dated zircon crystals up to 4.2 billion years old from rocks in Australia. It's by using that particular method. Okay, and you can see in the same laboratory that method was developed, those results came from that same laboratory that I just showed you. If you want the reference, it's in the first of the technical volumes of the rate research. Here's an example of granites. Now, granites have a number of minerals in them, and one of the minerals is the mineral zircon, which you've heard about from Russ Humphreys. Okay, it's zirconium silicate, and it's a mineral that doesn't usually melt. It's a very high temperature mineral. It's found in sediments, and sediments can melt to form a granite. And so if you've got zircons in the original sediment, they won't melt, and often the radioactive clock will not be reset. And so what you've got is a Himalayan granite that's supposed to be 21 million years old. It gives uranium lead ages of up to 753 million years because of having inherited these zircons from other sources. In a southeastern Australian granite that's supposed to be 426 million years old, you get uranium lead ages up to 3.5 billion years because of contamination of the granite with these supposedly old zircons. Similarly, in New Zealand, you get uranium lead ages of up to 1638 million years. Then a granite's supposed to be only 370 million years old. And you also, monazite is a phosphate mineral, but it has uranium and thorium in it. And you can actually get negative uranium lead ages in a Himalayan granite that's supposed to be in a monazite grain, a negative age, a granite that's supposed to be 20 million years old that gives a zircon age of 1483 million years. So the monazite gives a minus 97 year age, and the zircon gives a 1483 million years age.
So the negative age means it won't be formed for 97 by...
Correct, that's right. And this is actually part of my own research that I did when I was working with the mining company that brought me here to Denver in 1981. They owned the uranium deposit on which I did my Ph.D. research. And I was doing this research with one of Australia's government agencies, research agencies, and we were looking at soils. And of course, the soil over the uranium deposit was contaminated with lead from uranium decay. So that was quite obvious, and you can see those results down in the bottom left-hand corner there. But we also found that the soils up to 20 miles away, their lead concentrations plotted on an isochron line that lined up with the lead from the uranium deposit, which of course is absolute nonsense. So it just shows you that, in that case, the soils had obviously been contaminated by all the rocks that they were sitting on, and the age had nothing to do with the true age of either the soils or the rocks. Here we have some granites in southeastern Australia, where you can compare the neodymium isotopes and the strontium isotopes, and you actually show that the granite formed as a result of mixing of the isotopes from different sources of rock that melted to form the granites. So the isotopes again have nothing to do with the age. They have to do with other processes that have affected the parent-daughter relationship, in this case violated by crustal contamination. Everywhere we look, there's evidence of crustal contamination. So that violates the second assumption. And the third assumption, of course, is constant decay rates. Okay, constant decay rates. Now again, in the Grand Canyon, I said we have a number of rocks that we investigated during the rate research program. Go to the bottom of the Grand Canyon, you've got in the crystalline basement rocks, you've actually got metamorphosed basalt lava flows that are now called amphibolites. This is what they look like down at the Colorado River. They're a black rock like a basalt, but under heat and pressure they've been converted into a different rock with different minerals. And they're very common. In fact, in this photograph you can see to evidence, you can't quite see it because I've got a better photograph I should have up here that's got a marker on it. But if you see that label down the bottom, there's differences in that outcrop that indicate the bottom and top of the original basalt lava flow. It was originally horizontal, of course it's been tilted up vertically now, but you can see the top and bottom of what was originally a horizontal lava flow. These are basalt lavas. So how old are these amphibolites? Using the isochron dating method, we got a rubidium-strontium age of 1240 million years on 19 samples. Notice that? Not 4 or 5 that they usually use, the geologists usually use. Remember I said we went for overkill? 19 samples. Samarium neodymium, age of 1655 million years on 21 samples. And we got a lead-lead age of 1883 million years on 20 samples. Now, even with those error margins, those ages do not overlap. The plus or minus in the brackets is the error margin from the analytical error in the chemical analyses. And you can see there that none of those two ages agree, none of them overlap. They are distinctly different from one another. How is it that these three different methods on the same rock samples give three entirely different ages? If you go to the geological literature, they would argue that no matter what method you used on a rock, it should always give you the same age. That's why they usually only date a rock with one of these methods. They don't normally spend the money to do more than one method on the same rock. And so we deliberately, in this research program, chose to analyse each rock sample by more than one method to see whether the methods really did agree, whether the clocks had all ticked at the same rate in the past. So just to show you how we plot that, there's the isochron, the rubidium-strontium isochron. There's the samarium neodymium isochron, and this is the lead-lead isochron. And for those who are coming to Pittsburgh next month for the 6th International Conference on Creationism, I'll be presenting a paper on this in much more detail, a technical paper. This is what happens when you hit buttons. So when you plot these results on a diagram, down the bottom is what we call the present half-life. That's the decay rate, the measure of the decay rate. So uranium has a faster decay rate than rubidium, and samarium has an even higher, a slower decay rate. Okay, uranium decays faster than rubidium, which decays faster than samarium. And look at the differences in the ages. You can see that even with the error margins, they do not overlap. Why is it that these three methods should give such vastly different results? So we also found that the potassium-argon individual sample ages, that is the model ages, varied widely. In fact, in one outcrop, two individual samples from the same original lava flow, only a little more than 2 feet apart, one gave an age of 1,205 million years, the other 2,574 million years. Here's the outcrop, and we're looking at that dark rock in the middle of that gully. Okay, in the centre of one sample gave an age of 1,205 million years, less than 2 feet, just over 2 feet away, in the same outcrop, in the same original basalt lava flow, an age of 2,574 million years. Well, let's look at another. We mentioned the Cardenas basalt earlier. It's down in the bottom layers of the Grand Canyon. This is what it looks like from the south, from Desert View Tower. Those black rocks in that cliff there, they're all basalt lava flows. Here they are, up close and personal, and there's Steve in there, Steve Austin. We're in there collecting samples for this work. What kind of results did we get? We got a potassium-argon isochron age of 516 million years on 14 samples. The rubidium-strontium age I referred to earlier on 19 samples of 1,111 million years. Now notice that. The rubidium-strontium age is more than twice the potassium-argon age. And the samarium-neodymium age is more than 3 times the potassium-argon age at 1,588 million years. How can it be that these three methods can give such wildly different ages? And the potassium-argon single sample ages varied from 577 million years up to over 1 billion years. See, no two methods agreed. No two methods agreed. Now, when we plot these, that's where they sit. Now, notice something interesting here. Where we've got the rubidium and the rubidium and potassium, notice that the potassium decays faster. It has a present rate of decay which is faster than rubidium, and it gives a younger age. In fact, in every result we obtain in any rock unit, the potassium age was always younger than the rubidium age. Now, one thing I didn't mention before is that potassium and argon decay in a different mode to uranium and samarium. Uranium and samarium decay by what we call alpha decay, whereas potassium and rubidium decay according to a beta decay process. It's a slightly different type of radioactive decay. Notice, both in this diagram and the last diagram like this, and I'll show it to you again shortly, the alpha decay ages are always older than the beta decay ages. That's interesting. We actually started to see a pattern emerge in these results. So if you don't believe it, let's have a look at another example. Let's go to where the molten lava coming up from the mantle didn't make it all the way to the surface to explode as a volcano. Its progress was impeded, and it was forced out it hit a rock layer and then moved out horizontally, so it was squeezed like toothpaste between the rock layers and cooled under the ground. We call that a diabase sill. And here's an example in the canyon. You see that black rock there, not down at river level, but beneath that white streaky material, sloping up towards the skyline. That's a diabase sill, where the basalt rock, it was squeezed, when it was molten, was pushed sideways instead of going out through the top of a volcano. And here's another example in the further downstream of another one of these diabase sills, and we've actually put lines there to illustrate. This is nearly 300 feet thick. We actually collected a series of 11 samples from top to bottom because the composition of the rock changed as you went through that sill. And that's ideal for isochron dating because you've got to have a variation in composition. So what kind of results did we obtain for this diabase sill at Bass Rapids in the Grand Canyon? It gave a potassium-argon isochron age of 841 million years, a rubidium-strontium isochron age of 1,060 million years, and it gave a samarium-neodymium isochron age of 1,379 million years. By the way, we even took a single sample, separated it into its constituent minerals, and analysed each of the minerals to plot on a line, because that's an even more superior type of radioactive dating method. And then the lead isochron age was 1,250 million years. The model ages of potassium-argon model ages varied from 656 million years to over 1 billion years. So when we plot these results on the same diagram, notice again the alpha decay ages are older than the beta decay ages. The uranium and samarium ages are older than the potassium and rubidium ages. And again, the potassium age is younger than the rubidium age. The uranium age is younger than the samarium age. The faster the decay rate today, the younger the age. The slower the decay rate today, the older the age. Isn't that interesting? We saw a pattern in these results which gives us a clue that there's something systematically happening here to cause these different ages. Well, one last example. One of the granites in the Grand Canyon, the Ells Chasm granodiorite. And this is one of the Ells Chasm granodiorite there, that grey rock. It gave a rubidium-strontium isochron age of just over 1,500 million years, samarium-neodymium age of over 1,600 years, and a lead-lead age of nearly 2 billion years. The error margins are a bit larger with this rock, and so there's a little bit of overlap, but still the pattern is there, except in this instance, the uranium age is older than the samarium age. But some of the labels are in the wrong place there. The rubidium age, those should be up higher. The rubidium age is still younger than the samarium and the uranium. So let's try and, I've got one more example here. Somerset Dam. It's where the basalt magma, and this actually comes from where I live on Australia's east coast. Brisbane, city of Brisbane, about 1.5 million people. And Somerset Dam is actually one of the water supply dams for the city of Brisbane. And there's a place there where the molten rock has cooled under the ground in a larger mass of rock. And it's actually layered with different varieties of this original rock. And there's Snelling, one of the Snelling juniors that was helping me on a field trip. Okay. We get a potassium-argon isochron age of 174 million years, a rubidium-strontium age of 393 million years, and a samarium-neodymium age of 259 million years. A lead-lead isochron age of 1,425 million years. Again, different methods on the same rocks giving you widely varying ages. Okay, let's sum up. But shouldn't the different methods on the same rock yield the same age? I mean, that's what the textbooks say. They're all clocks that are supposed to measure the true ages of these rocks. Yes, if the three assumptions are correct. All